Good morning. Good morning. Hope all is well. Hope everyone's doing all right. We'll take a few seconds to let everybody get in who's coming, and then we'll get started. All right. So last class we closed out 5.2. So we're looking to get into 5.3 today. Anybody have any questions on anything? Any concerns before we get started? All right. Seems like everybody's okay. Okay. So looking at 5.3. Independence and multiplication rule. See if I can write this a little better. All right, so two events are independent if the occurrence of one event does not affect the other. All right, two events are dependent if the occurrence of one event does affect the other. All right, so the first exercise we're looking at is establishing whether two events are independent or not. So it says, suppose you flip a coin and roll a die. Are the events obtain a head or roll a 5 independent? All right. So yes, these events are independent. One has nothing to do with the other. So flipping a coin and rolling a die does not alter any of the outcomes. So of course, we'll see an example of what it means for events to be independent, to be dependent, but these two events are independent. Mhm. Are the events earned a bachelor's degree and earned more than $100,000 per year independent? All right. So these are not independent because earning a bachelor's degree increases your chance of earning $100,000 or more. So it does not secure or make it 100% guaranteed that you will earn $100,000 or more. It just increases your chances. So, and that's what we're talking about here. If anything alters the probability or the chance of something occurring, then those events are not independent. All right. Any questions before we go to the multiplication rule? Scrolling up. It's okay. So remember last section we were dealing with the probability of your event E or F occurring. This time we're looking at the probability of E and F occurring. So we're talking about both of them occurring, not necessarily one or the other. So last section, that was the addition rule when you're looking at the probability of one or the other event occurring. In this case, we're looking at the multiplication rule where we're looking at both of them occurring, E and F, or both, both of your events. So here, probability of independent events, you would take each probability and multiply them together in order to find the probability of both of them occurring. All right, scrolling up. Anybody still copying the multiplication rule? All right. So let me erase this. So in the game roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot number 17 2 times in a row? All right, so these events are independent, so you do need to establish whether they're independent or dependent. Remember, this is for, still have my original on. This is for independent events. So you do need to establish whether these events are independent or dependent. These events are independent because the occurrence of rolling the 17 does not affect the rolling the 17 again. So in other words, when I roll the ball and let's say it hits 17, we're not leaving the ball there. We're going to take it and roll it again, take it out and roll it again. There's not a block there to stop you from rolling 17 again or stops or take away any of your other options. So the probability stays the same and the occurrence of rolling 17 is not affected by rolling 17 a second time, the first time. So we look at our, remember whenever we're trying to do a probability, we need our sample space. Our sample space is, if I can get my pen right, 0, 00, and then 1 through 36. So we have 38 numbers to pull from, 0, 00, and then 1 through 36. 17 only appears once. There's only one 17 on the wheel. So the probability of getting a 17 is 1 out of 38. Okay. So since they are independent, that means we just take those probabilities of 1 out of 38. We talk about 17 twice. So it's 1 over 38 times 1 over 38. And that'll be 1 over 1444, which is 0.0006925. And of course, MathLab will ask you, will let you know which one they want from you. All right, questions on that before we go to the next example? All right, let's scroll up. Let me know if I go up too far. Anybody still copying the blue? All right. Can I get this whole thing in here? Yep. All right. So next example, and I'll give you a chance to write it out. The probability that a randomly selected 24-year-old male will survive the year is 0.9986, according to the National Vital Statistics Report. First question, what is the probability that 3 randomly selected 24-year-old males will survive the year? Then the second question, what is the probability that 20 randomly selected 24-year-old males will survive the year? So I'll give you a chance to write it out for those who are doing so. All right. So are the events independent? The answer is yes. The fact that one male, 24-year-old male survives the year has nothing to do with another 24-year-old male surviving the year or not surviving the year. So these are independent events. So we saw that the probability of that male surviving the year, 0.9986. Sorry about that. Knock something down. All right, and then the probability that all 3 survive the year, since they are independent, is just multiplying all 3 together. And so it's 0.9958. So basically you would just take 0.9986 and raise it to the 3rd power. And it'll give you 0.9958. Any questions before we go to B? B was a probability that 20 would survive the year. And you're just going to take that 0.9986 and raise it to the 20th power, which will give you 0.9724. So depending on the calculator that you have, you'll either use that little hat symbol with, look like it's part of a triangle right here. Or you have this button where you can put a number in the larger box, which would be 0.9986, and then put the 20 as your exponent in the smaller box, your exponent. Either way, just make sure you know how to use your calculator. And if you have any questions on how to use your calculator, make sure you bring your calculator to class so we can, or office hours, and we can make sure that you're straight moving forward. Questions before we look at the next one? All right. So next one, compute the probability that at least one male out of 1,000 24-year-olds will die during the course of the year if the probability that a randomly selected 24-year-old male survives the year is 0.9986. All right. So because we're looking at the probability that 1,000, well, at least one male out of the 1,000 will die versus survive, we're going to have to use the complement rule. All right. So the way that will work out for us is that if you talk about at least one dies, then we need to find the probability that none will die. Because when we say at least one, that means it could be 2, it could be 3, it could be 4, it could be all 1,000. But none dying is the complement of at least one dying. So we would take the success or the probability of someone living at 24-year-olds is 0.9986. So if you multiply that times 1,000, that's the probability of all 1,000 living or surviving the year. And that's 0.2464. And then if you subtract that from 1, remember to find the complement, that's everything else. You subtract it from 1, and that'll give you 0.7536. Questions on that? So everybody okay with what happened? So that's it for 5.3. Any problems before we go to 5.4? All right, done copying. All right, so last section for today, and that's actually the last section out of chapter 5. It's the conditional probability and the general multiplication rule. Before we looked at the multiplication rule for independent events, this is the general multiplication rule. All right, so conditional probability, we have this, the probability of F, and then we have slash E. It's like really like a straight line more than slash. It's the probability that F occurs given that E has already occurred. So that line between F and E represents given that, or F given E. So it's the probability that F occurs given that E has already occurred. And here's how we would calculate it. Take the probability of E and F and place it over the probability of E. Or if you have the number of E and F over the number of E. Number of outcomes, I should say. Excuse me. Tried to hit the mute button, couldn't catch it. All right, scrolling up. So we have a chart here. Everybody holding on to the formula? All right. So this is the marital status of males and females 15 years or older in the US, and this is in millions. So categories, we have, as far as marital status, never married, married, widowed, divorced, separated. Then on top, you see males, females. Of course, we have totals in both cases. So I'll give you a chance to write that down. All right, so we use the table to answer the following questions. Anyone still on the table, scrolling up? Okay. So first question, compute the probability that a randomly selected individual has never married given that the individual is male. So never married given the individual is male. So these things do matter. The positioning does matter because remember, when we look at our formula, if you're talking about F given E, E is down here on bottom, not F, and then it's E and F. So the top doesn't matter because it's always going to be both variable, both events, but the bottom one matters. And that is based on this one right here. So just want to throw that out there when we get to it. All right. Then the next one, compute the probability that a randomly selected individual is male, given the individual has never married. So it's just basically flipping them and then showing you that the order does matter. So once again, give you a chance to write that down for those who are writing. All right, so I'm going to call N never married and M male just to shorten it up. All right. So the first one, we want the probability that the person chosen never married, given that he was a male. So up top is going to be both of those events, and on bottom is going to be male. So we go to our chart, looking for never married and male, that's 41.6. And then for the males, number of males is 122.5. So that's what we did here. And it's a 0.34 for our probability. All right, any problems with that? All right. So the next one is very similar, it's just that they flipped the order. So before it was never married, given that the person's male. This time is person's male, given that the person was never married. So once again, this top number stays the same because he's talking about being married and never male and never married. Male and never married, or never married and male are the same thing. But then our bottom number is going to be different because this number is second, or this event is second. So we look for the number of people that are never married. And that's right here, 78.5. So that's 41.6 over 78.5, and that'll be 0.53. All right, questions? Any questions? All right, scrolling up. Suppose that 12.7% of all births are preterm. Also, 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? And then, is this unusual? So, as always, give you a chance to write that out. All right. All right. So gonna call W weighs 8 pounds, 13 ounces or more. Call P preterm. So we know the probability of getting a preterm baby is 12.7%, converted to decimals 0.127. And then it also tells us probability to have a baby that's preterm and weighs 8 pounds, 13 ounces or more, 0.22%, converted to decimals 0.0022. All right. So probability that a baby weighs 8 pounds, 13 ounces or more, given that it's preterm. So you do P and W over probability of P. So that's 0.0022 over 0.127. So 0.0173, that's 1.73%. You will convert it back to a percentage. And so the question was, is this unusual? The answer is yes, because the probability is less than 5%. Remember, we said that was our marker for unusual probabilities. All right, questions. Everybody good? All right, so there goes the general multiplication rule. I'm going to take the probability of E and multiply it times the probability of F, given that E has already occurred. All right, so the probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? All right, so once again, I like to start off with labeling my events, just to shorthand what's going on and be able to establish what numbers go with which. So I'm calling T gets a ticket, P for pulled over. So the probability that someone gets pulled over, I believe when they're speeding, yep, driver speeding gets pulled over is 0.8. Then the probability that a person gets a ticket given that he or she is pulled over is 0.9. All right. So the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket. So here it is. Probability the person gets pulled over, then the probability the person gets a ticket given that that person was pulled over. That's 0.8 times 0.9, give you 0.72. All right. Problems. I think we got one more. Any questions before we go to the next one? All right. Got a little more, but this is the beginning of it. So in a study to determine whether preferences for self are more or less prevalent than preferences for others, researchers, excuse me, ask individuals to identify the person who is most valuable and likable to you or your favorite other. Of the 1519, 100, well, in other words, 1,519 individuals surveyed, 42 had chosen themselves. So out of the 1519, 42 chose themselves as the one they like to be around the most. I'll give you a chance to write that down. Then we have 2 questions, might be 3, that pertains to this study. Okay, the first one, suppose we randomly select one out of the 1,519 individuals. What is the probability that he or she had chosen self as a favorite other? All right. So once again, suppose we randomly select one out of that 1519. What is the probability that he or she had chosen self as a favorite other? So we know altogether we have 1,519 people. Out of that 1,519 people, 42 chose self. So the probability of getting someone or picking someone who chose themselves as their favorite other is 42 over the 1519. So that's just basic or foundational probability, number of your event over the number of your sample space. All right. All right. So for B, if two individuals from this group are randomly selected, what is the probability that both chose self? So we want to know the probability that the first one chose self and the probability that the second person chose self. So that means the probability of the first person choosing self times the probability that the second person chose self, given that the first person chose self. So you got to remember when you're picking this person out, it didn't say with replacement. It's not like you're putting the person back into the group that you chosen from. So you have to consider the alterations that has occurred. All right. So we know the first probability is going to be 42 out of the 1519 because there's 1,519 people altogether. Out of that group, 42 of them have chosen self. Now, once you take that one person out, the top number is going to be one less and the bottom will be one less because now in the group, there's only 41 people left that chose self. And now totally in the group, there's 1518 instead of 1519. And so, those my purple notes here, just emphasizing what we're talking about. So the 41 and the 1518 comes from what was left from the group originally. There's only 41 people left that chose self, and then there's 1,518 people left altogether from the survey. All right. So then you go ahead and multiply those together. And that'll give you 0.0007468 as your answer. Any questions? Any questions? All right. Last one. Compute the probability of randomly selected two individuals from this group who select itself, assuming independence. So we're going to assume that the probability doesn't change, that choosing one out of the group has nothing to do with choosing the next person out of the group. So before they were dependent, in B they were dependent because when I chose one out, we have to consider the fact that I didn't put one back. So it's still that 42 goes down to 41. 1519 goes down to 1518. But if we're assuming independence, that means when I pick a person out, it doesn't change the probability for the next choosing. So this means 42 over 1519 will stay the same in both cases. And then you just multiply those together. That'll give you 0.007645. Any questions? Any questions? Concerns, comments, anything, anybody? Okay. So that is it for chapter 5. That's 5.1 through 5.4, where we did 5.1, 5.2 last class, 5.3, 5.4 this class. So that's it for chapter 5. Chapter 6, if I'm not mistaken, is only 2 sections. Yep, section 1, section 2. So of course, we're not going to get into that today, but make sure you guys are staying up on your work, and ask some questions if you have them. And don't forget, we have 2 tests that are posted, and this third one, we'll talk about it next class. I need to map this thing out, see if we have time for it. It may be proctored, but we'll talk about it in next class, and then go from there. But any questions, concerns, or comments about anything before we go into the weekend?
No, none at all.
All right. Thank you. Well, appreciate you guys tuning in. Have a great weekend, and I will see you next class.
You too. Thank you so much.
Thanks.
Have a good day.
Thank you. The same. Take care.